In the present video we are going to investigate, why did India's Chandrayaan-2 mission fail to land Vikram lander on the surface of Moon? Before we analyze, let us look into the components of the lander. The Vikram's propulsion system consisted of 850 Newton thrusters for attitude control and 5 800 Newton liquid engines for braking. It also had 4 reaction wheels and associated electronic controls to drive them, and 2 microstar sensors to measure the moving velocity of the lander. It had lander position detection camera, lander horizontal velocity camera, cabin altimeters, laser altimeter, touchdown sensors, lander hazard detection and avoidance camera. With the help of all this machinery, Vikram was designed to soft land on the surface of Moon, and capable of communicating with IDSN at Beelalu near Bangalore, as well as orbiter and Pragyan rover. The descent of Vikram lander consisted of 5 phases. 1 rough braking phase, 2 absolute navigation phase, 3 fine braking phase, 4 hovering phase or retrograde phase, 5 landing phase. The rough braking phase started from the Vikram's parking orbit at 35 km altitude. It persisted until it reached an altitude of 7.4 km above the surface of Moon. During the rough braking phase, 4 800 Newton liquid engines operated to reduce the velocity of the lander. The rough braking phase is followed by the absolute navigation phase, also called as the cam coasting phase. It started at 7.4 km altitude, and persisted until the lander reaches an altitude of 5 km. I suppose the aim of absolute navigation phase is move the lander towards the landing site. This is accomplished by scanning and identifying the landing site, and change the attitude of the lander and engine throttle to navigate towards the landing site. During the absolute navigation phase, 4 800 Newton liquid engines operated along with a 50 Newton thrusters for attitude control. Fine braking phase followed the absolute navigation phase. It started at an altitude of 5 km, and continued until the lander reaches an altitude of 400 meters. During the fine braking phase, 4 800 Newton liquid engines operated along with a 50 Newton thrusters for attitude control. Fine braking phase was followed by the hovering phase, during when the lander was designed to vertically descend for the touchdown. This phase starts at an altitude of 400 meters, and continued until the lander reaches an altitude of 10 meters, during when the 2 800 Newton liquid engines were at operation. The final landing phase consisted of the vertical descent of the lander from 10-meter altitude until it touches down on the Moon's surface. During the landing phase, the 5th engine of the lander was at work. The total landing phase was planned to last for a duration of 15 minutes, during when the velocity of the lander is supposed to reduce from 1,680 meters per second to almost 0 meters per second. However, actually, the landing phase lasted only for a period of 13 minutes. As it fell short by 2 minutes, the velocity reduction that is supposed to happen during the last 2 minutes did not occur at all. As a result, the lander almost straight fall to crash land on the surface of the Moon. We will now investigate the possible reasons of the deviation from the planned trajectory. 1. Engine failure hypothesis. As the lander crash land on the surface of the Moon instead of soft landing, we can speculate that one or more of the engines malfunctioned during the last 2 km altitude. Here we should not forget that the engines were reducing the velocity of the lander. If there is engine failure, that would have resulted in higher horizontal velocity in addition to the vertical velocity. Higher horizontal velocity would have been apparent, because at an altitude of around 2 km the lander was still oriented at an inclination between the horizontal and vertical axes. If that is the case, the engine failure would result in increased trajectory length instead of a shorter trajectory. However, in the actual trajectory of the lander, the flight path becomes shorter with a sharper angle. So, this explanation excludes the possibility of engine failure as causative factor for the crash landing of the Vikram lander. 2. Attitude failure hypothesis. During the fine braking phase between 5 km and 400 meter altitude, the orientation of the lander is anticipated to change from an inclined angle to almost vertical angle. Because the hovering phase that follows after the fine braking phase is a near vertical descent. Let us speculate if the lander for some reason started orient in the middle of the fine braking phase in an opposite inclination. Such a scenario would possibly lead to a reduction in the trajectory path. This is because the engines will reduce the velocity of the lander at a higher rate than the planned. The same was evident from the actual trajectory, that was 2 minutes shorter than the planned trajectory. Although this appears to be a plausible explanation for the crash landing of Vikram lander, we should not forget that the flight trajectory graph that we have is an indirect evidence only. If we have to conclude the attitude failure is the cause of the crash landing, we need to find the inclination angle of the lander at around 2 km altitude from the log file of the lander's computer. What we would do differently, if we are redoing the moon landing all over again. 1. Better software system. I suspect this failure may be as a result of a software glitch. If we need to improve on it, we may have to have a true closed-loop feedback throttle and attitude control. I suppose in the failed Vikram lander, a variable thrust propulsion and attitude system was implemented to reduce the velocity of the lander based on mathematical or theoretical modeling or predictions. Let us assume if we would have implemented a dynamic closed-loop feedback throttle and attitude control system based on the rate of descent and inclination data of the lander would self-correct itself for the unanticipated errors. We would maintain the throttle level of the engines and thrusters until the dynamically calculated rate of descent and inclination of the lander is in the acceptable range for a particular altitude. 2. There was no real-life testing of the landing. Ideally, a soft landing would have been tested in the planet Earth, before the project would have been cleared. A small weight like 100 kg along with an engine system and the software control, that had correction factors for the gravity of Earth versus Moon would have been used for testing. In other words, a scale model of the lander would have been dropped from a height of about 10 km using an aircraft and made to soft land on the Earth at least couple of times. This would have taught us big lessons at a lower cost. The approval committee would have asked for this data before approving the mission. No matter what an extent of theoretical simulations or mathematical modeling used to design the software control system goes inadequate, however, 1 or 2 real-life experimentation would teach a lot of lessons.